In this video, we're going to talk about techniques for computing limits. This will be part 1 of 2. We'll come back to part 2 in our 6th video. And we are going to talk about continuity between those two topics. So let's go ahead and get started here. Our objectives for this video are to discuss techniques to compute limits conceptually, to compute limits and state limit laws used to justify computations, to evaluate two-sided limits using limit laws and theorems, to evaluate one-sided limits using limit laws and theorems, to evaluate limits using factorizations, and to identify and discuss important limits. Specifically, we'll be looking at exponential functions. I may also mention some stuff about logarithmic functions when we get there, since they're another special type of function that you will talk about in your calculus class. So first, let's look at limits of linear functions. We have developed a conceptual understanding of limits, but many situations will arise where either our previous techniques will fail or we won't have a visual graph readily available. So in this section, we'll learn some analytical methods for evaluating limits. Specifically, we'll look at direct substitution first, and then we'll look at algebraic manipulation, like factoring or multiplying by the conjugate. Hopefully you have a lot of practice from both from pre-calculus of both factoring and multiplying by conjugates. So we usually use our algebra techniques with factorization there. And we'll also have direct substitution. Let's look at linear functions, our most basic type of function here. So we're going to let a, b, and m be real numbers. For a linear function, y equals mx plus b, the limit as x approaches a of f of x is equal to f of a is equal to m times a plus b. So this is direct substitution here for the value x equals a. And let's just look at an example here. If we have our linear equation there, y equals mx plus b, that goes through 0b and has a slope of m. Then we can pick a point out here anywhere that we'd like that we call x equals a. And that point there is going to be a f of a. F of a will be there on the y-axis. We can see that as we approach from the left and from the right, that as we get close to the value of x equals a, we're getting close to the y value of f of a. And f of a is going to be equal to ma plus b. So in fact, you're able to find f of a for a function f of x for limit as x approaches a of f of x equals f of a for most basic functions that are continuous functions. And we'll talk about this idea of continuity next lecture video. This will be topic 5. Okay. Limits of linear functions. We're going to just use direct substitution here. And let's make a direct substitution here. that. And this is a constant function. Y equals 5. So no matter what x is or what it approaches, it's going to equal that constant 5. You can go ahead here and look at this function. Do a rough sketch here of this. We might have 1, and then over here we might have 50, and then 100. We have this line up here, y equals 5. No matter how close I get to 100 from the left or the right, it's this value right here of 5, 100 that I'm getting close to. All right, we've got some limit laws here. So let's go ahead and take a look at those. Assume that the limit as x approaches a of f of x and the limit as x approaches a of g of x exists. I'm going to call this first limit a capital L and the second limit a capital M. To shorthand these, the following properties hold true when c is a real number and n greater than 0 is an integer. So first is the limit of a sum, and that's the sum of the limits, L plus M. The difference, the limit of the difference is the difference of the limits, otherwise known as L minus M. If I take a constant multiple c times my function f of x and take the limit of it, then the c can pass through the limit symbol since it doesn't contain any x's, and this is going to be c times L. The limit of the product is going to be the product of the limits, L times M. And the limit of the quotient is going to be the quotient of the limits, L divided by M, provided that M is not equal to 0. The limit of the function raised to a power is that limit raised to that power, L to the n. Remember that n has to be greater than 0 and is an integer here. Actually, we'll find out that it can be any power later, but if it's negative, then we have a problem that the limit here can't be 0, so that I don't divide by a 0, and I don't want a negative in here if this power is fractional, which is the next rule, that if I have a fractional power and n is even, then I can't have a negative on the inside. My function has to be greater than 0 near x equals a. Might say we'll talk about this root 1 later in the notes, and just note that product and quotient, even though when we talk about derivatives that they're big limits, these properties are not inherited. These two for product and quotient, not inherited by derivatives. Derivatives will have their own product and quotient rules. A lot of the other rules here for sum, difference, constant multiplier, and so on will all be inherited by derivatives. This is going to be the nth root of L, is what this one is going to be. So let's give you some information here about a function. Not going to give you the function, but suppose that the limit as x approaches 2 of f of x is equal to 4. Limit as x approaches 2 of g of x is equal to 5. Limit as x approaches 2 of h of x is equal to 8. Let's go ahead and find the limit as x approaches 2 of f of x. minus the limit as x approaches 2 of g of x, and all of that divided by the limit as x approaches 2 of h of x is going to give me a 4 minus 5 over 8 is a negative 1 over 8. Okay, so we have limit as x approaches 2 of 6 times f of x times g of x plus limit as x approaches 2 of h of x. So this is going to be 6 times the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x plus 8. 6 times 4 times 5 plus 8. 20 times 6 is 120 plus 8 is 128. This is going to be limit as x approaches 2 of g of x raised to the third is 5 to the third is 125. And just note, when given expressions for f, g, and h, direct substitution will give these answers also. So you don't have to be told what the limit is. You may need to calculate that limit. So again, we're starting to use words that we're really going to define next time, but polynomial functions are special because they are continuous over their entire domain. As such, if f of x is a polynomial, then limit as x approaches a of f of x equals f of a. We'll talk about why that is next time, what that means to be continuous. Rational functions, the ratio of polynomials typically contain discontinuities. In the form of poles or vertical asymptotes. Therefore, when evaluating the limit of a rational function, be cautious of problem spots that are not in the domain. Limit as x approaches a of f of x over g of x. This limit is equal to f of a over g of a only if g of a is not equal to 0, because division by 0 is invalid. Let's cover up this theorem number. It's not the theorem number in your textbook, but it is a theorem in your textbook, just maybe with slightly different wording. So limits of polynomial and rational functions, assume p and q are polynomials and that k is a constant. For polynomial functions, the limit as x approaches k of p of x is equal to p of k. And for rational functions, the limit as x approaches k of p of x over q of x equals p of k over q of k, provided that q of k is not equal to 0. If q of k is equal to 0, we'll use other techniques. We'll use algebra techniques. So let's go ahead and look at the limit as x approaches 2 of 3x squared minus 4x over 5x cubed minus 36. So we're going to try direct substitution here. This is going to be equal to 3 times 2 squared minus 4 times 2 over 5 times 2 cubed minus 36. It's 3 times 4 minus 4 times 2 over 5 times 8 minus 36. It's 12 minus 8 over 40 minus 36. 4 over 4 is 1. Now we have another example here for you. Limit as x approaches 4 of x squared minus 9 will be 4 squared minus 9 is 16 minus 9 is 7. So first one was a rational function. This one is a polynomial. Example there. All right. Let's go ahead and look at one that's maybe going to take some algebra. Let's try direct substitution first. So by direct substitution, we have square root of 2 times 2 cubed plus 9 plus 3 times 2 minus 1 over 4 times 2 plus 1 is equal to 2 times 8 plus 9 plus 6 minus 1 over 8 plus 1 is 16 plus 9 plus 5 over 9 is square root of 25 is 5 plus 5 over 9 is 10 over 9. So later we'll have to be careful with functions that include square roots, and we'll probably need to use conjugates most of the time. So note that we have not actually evaluated limits where the denominator of a rational function is 0 yet. When we do, we'll use some algebra. To do that, we'll simplify by factoring if possible. Or we'll multiply by some form of 1. To change the way the expression looks, but not necessarily change the expression itself. Might also be called upon to that you'll use identities. Identities usually have to do with trigonometry things. You might know some other identities later in this class, though. But I highly doubt you're going to use identities. That's another algebraic technique that's more for calculus with analytic geometry, which is Math 263. So one-sided limits, let's consider the function f of x is equal to the square root of x, and I'm going to draw that parent function here. What happens is x gets close to 4 here. I'm coming towards the square root of 4 is 2, and that's from the left and the right, so that limit is going to exist. What if I try and get close to 0, though? Well, that limit does not exist. This is a special case because there is no limit from the left here. So remember that for a limit to exist, the limit as x approaches a from the left has to equal the limit as x approaches a from the right of the function. So let's talk about those one-sided limits there, what it means to come from the left and the right. So specifically, we're going to look at one-sided limits for roots here. Again, just going to cover up this theorem number because it is not your theorem number in your textbook. It's from a different textbook. So limit laws for one-sided limits for roots. The limit as x approaches a from the right of f of x of 1 over n is equal to the limit as x approaches a from the right of f of x of 1 over n, provided that f of x is greater than or equal to 0 for all x near a with x greater than a. If n is even, if n is odd, then really this can take on any value that we want it to, because we can take an odd root of any positive, negative, or 0 value for that function. Similarly, if limit of x approaches a from the left of f of x raised to the 1 over n is equal to limit as x approaches a from the left of f of x to the 1 over n, provided that f of x is greater than or equal to 0 for any x value near x equals a with x less than a if n is even. So these rules only have to do with if n is even. So what about this function limit as x approaches 0 of the square root of x? Well, we don't, it doesn't exist, right? So does not exist. Like we said, this is a special case where I am approaching that initial point in the domain. The reason we don't care about odd roots is, let me draw it out, that they look kind of like this parent graph for the cube root of x, or something like that. Y equals the cube root of x, and it is going to be continuous everywhere. We don't have a problem of approaching from the left and the right anywhere here. So limit as x approaches 0 of the cube root of x is equal to 0. Looking at this graph, that's 0, 0 right there, and I approach from the left and the right where it's continuous, I can do direct substitution and figure out the limit of the cube root of 0 is 0. So you need to think of tracing the graph through pencil and approaching x equals a from both sides. Both directions. What value are you approaching? You cannot trace the square root of x from the left because there is no graph over there to the left of 0. So now let's look at piecewise defined functions. F of x is going to be equal to a negative 2x plus 4 if x is less than or equal to 1. And it's going to be equal to the square root of x minus 1 if x is greater than 1. So let's find values of f of x for the limit as x approaches 1 from the left of f of x is going to be this first piece. Limit as x approaches 1 from the left of f of x is equal to negative 2 times 1 plus 4 is a negative 2 plus 4 is a positive 2. And the limit as x approaches 1 from the right of f of x is equal to plug that 1 in for the x using direct substitution into this piece that comes from the right is going to be the square root of 0 is 0. Let's see if I can draw a little picture here. for you. Do my best here. Limit as x approaches 1 is from the left is going to be 2. And we have a y-intercept of 4. That slope is a -2. All right. So limit as x approaches 1 of f of x does not exist because we do not approach the same thing from the left and the right. It's what we call a jump discontinuity. Let's apply our rules here for limits for one-sided limits. So as I get close to 0 from the left, well, that doesn't exist on my graph, so I don't know. 0 from the right, coming towards 3. 1 from the left, we're getting towards 4. 1 from the right, we're getting towards 4. And because I'm approaching the same thing left and right, that limit as x approaches 1 is also 4. Limit as I approach 3 from the left is 0. 3 from the right is going to be 1. And this is not going to exist because they have different limits from the left and the right. As I approach 2 from the left, I get 3. As I approach 2 from the right, I get 3. And so the limit as I approach from the left and the right is 3. Ignore that f of 2 is equal to 2. Don't try direct substitution. Right? Like I already mentioned, we'll come back to this example when we discuss continuity in lecture 5. It'll be important that you explore further how these concepts are related. So let's go ahead and let's look at some other techniques for evaluating limits, specifically factoring and cancellation and general algebra, and then the use of the conjugate. So in general algebraic simplification, will be used where direct substitution fails. It'll be your next go-to technique. And the above listed techniques for factoring, canceling, and using the conjugate are two of the most common that you'll use. So let's do some examples of both. First, let's start off with this rational function, and we're going to try direct substitution. If we can here, just to show that we get 4 minus 24 plus 8, I'm sorry, 4 minus 12 plus 8 is a 12 minus 12 is 0. Over 2 squared is 4 minus 4 is also 0. And 0 over 0 is going to be something that we're going to talk about in the later videos here. It's called an indeterminate form. It's going to be abbreviated by I period F period. We'll use something special to deal with that type of a limit later. Right now, though, let's take a look at the picture here. X equals 2, x equals -2. Actually, we have x minus 2, x minus 4, x minus 2, x plus 2. So this asymptote isn't there. Instead, we have 2, -2 over 4. So -1/2. Open circle there. I see a horizontal asymptote here of y equals 1. Is that ever equal to 1? Yes, it is. That was 0 where I drew the line, not 1. Need to fix that. There we go. And just to solve to see where it crosses that asymptote, x squared minus 6x plus 8 equals x squared minus 4. So negative 6x equals a negative 12 and x equals a positive 2. So when x is a positive 2, then that doesn't make a whole lot of sense. All right. We already know when x equals 2 that the function is 4 minus 12 is negative 8. That's 0 over 4 squared minus 4 is also 0. 0 over 0 is going to give us a hole in the graph. At negative 2 over 4 is a negative 1/2, so I'm good there. So I don't think this is ever going to cross because it says that it thinks that it crosses here at x equals 2, and that doesn't happen. Do have a x-intercept here that I'll find. It's going to be 4. I think this is going to come in from the bottom. We get close to no asymptote over here on this side. Negative 2 for my y-intercept. It's going to come down this way, up this way. And then if I compare everything, the simplified version that I got here of x minus 4 over x plus 2 is it agrees at every point other than this one point right here, which it fills up because I didn't leave the 0 in the denominator there since I'm getting close to but not touching that point. So I can use that simplified version with that hole filled in to tell me what the limit is going to be as I approach that point. I want to find limit as x approaches 2 of f of x is going to be equal to a negative 1/2. All right. Let's talk about conjugates for a second. So what is a conjugate? Remember two things from pre-calculus, that a plus b times a minus b is equal to a squared minus b squared. So if I have a funky square root that I want to get rid of, multiplying what's called by what's called its conjugate pair, we'll get both pieces to be squared, and you'll find the difference of squares, and it'll get rid of the square roots most of the time. So let's go ahead and also remember that for ax squared plus bx plus c equals 0, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, and that this plus or minus here, these two answers are conjugate pairs. All right, let's try that with this first one. If I try direct substitution first, it's going to fail. It's square root of 1 minus 1 over 1 minus 1. 1 minus 1 over 1 minus 1 is 0 over 0, which we need more info. So let's go ahead and let's multiply top and bottom, or if you know how to factor, you can do that. Limit as x approaches 1 of square root of x minus 1 tells me I want to multiply top and bottom by square root of x plus 1. X minus 1 times square root of x plus 1. And then it's going to leave me with square root of 1 show you what's going to equal first. Square root of x minus 1 times square root of x plus 1 is an x minus 1 that cancels out with this x minus 1, leaves me with the square root of x plus 1. This is still limit as x approaches 1 here. It's going to be 1 over root 1 plus 1 is 1 over 1 plus 1 is 1 over 2. Very important to do this, especially when we have limits of difference quotients. They'll be called derivatives for radical functions later. All right. Let's look at our last section here in this set of notes. Important limits, limits of exponential functions. So direct substitution can work for both types of exponential functions that we're going to have that are in the form of y equals e to the x and y equals a to the x here. Because we're evaluating finite limits. However, algebra can be required sometimes to help us out. So evaluate limit as x approaches 0 of 2 to the x is going to be 2 to the 0 is 1. Limit as x approaches 0 of e to the x is equal to e to the 0, which is also 1. Anything a to the x, including e to the x, is a graph that looks like this. That has to go through the point 0, 1, unless I do some other transformations to the graph. So if we were going to do a limit as x approaches 4 of e to the x, that would give us e to the 4th power, and we'd approximate that with our calculator as 54.6. So later we'll be taking the right-hand limit of this or the left-hand limit of this, those one-sided limits, and we'll be interested in something like limit of e to the x as x approaches infinity. And you can see the right-hand behavior that goes to infinity. Limit as x approaches negative infinity of e to the x will be going towards 0, this horizontal asymptote on this side. more on that later. I believe that is it for this video. We'll come back next time and talk about continuity. Then when we come back after that, we'll talk about the second part of techniques for computing limits. See you for the next video.